the recording. So we are talking today about ANOVA. We finalized ANOVA today. We're getting them next week. No, we're getting on Wednesday towards correlation. And on Monday, we're going to do linear regression. So likely we will push some of the linear regression towards Wednesday. So that's why I also wasn't necessarily opposed to doing on Wednesday the quiz. But essentially, we're doing quiz 2 on T distribution only up until 11:28. In quiz 2, we're doing then homework 3 comes up practice lab 5. This is correlation and regression. And then quiz 3 will span ANOVA, correlation and linear regression. Chi-squared will be the only thing you have never written a test on when it comes to the final. Chi-squared will only be with the final. Yep.
That's 14.
14 is the two-way ANOVA, which I'm sparing from the material. This will not be quizzed because
17 and 18 is the
17 and 18. 17 is the chi-squared. 18 is I forget the exact chapter name. This is basically an overview, a repetition of all, which will be. Yeah, no, they will review for finals. I usually discuss chapter 18 and review for the final, which basically it's revisiting all the topics in a way. When do you use which test and how, what prompts you to use that test? That's actually only a summarization chapter. And I will do that with review for the final. So, but the chi-squared will only be on the final, will not come to any of those quizzes.
So what chapters are going to be on the final on that? Like
all of them except all of them minus 14.
So up until
1 to 18.
So 18, not 21, not 21 or
no, chapter 1 to 18. All the modules.
So what chapter? Including 21.
Yes, and so the review for the final, we're just repeating all the chapters. So I usually use chapter 18 to go through all individual questions and PowerPoints and all methods again. So this is a pure review session. And this is really just meant to, like last time, like give you a quick walkthrough what the respective chapters were about, what you need to remember. And I'm going to pinpoint what's important that you 9 days later, you're going to ace that exam, which is, please do not underestimate the final. I just can reiterate it. It's a lot of stuff. Wait, if you had a question? No? Yes. Quiz 3 is going to be ANOVA, between groups, within groups, and then we have correlation and regression. That is 12, 13, 15, and 16. Yep. Correlation and regression, you're going to like that because it's very intuitive. I'm a big fan of regression. You're going to like regression, I'm sure. Okay, any other questions? Anything concerning the syllabus, the quizzes? You've seen the quizzes. They're not terribly hard, right? You're going to do fine. All right. If no further questions, then let's go back to ANOVA. So we have discussed last time our ANOVA between groups. One-way ANOVA between groups. So again, keep in mind, you're employing an ANOVA over a t-test when you have 3 or more groups. So 3 or more levels in an independent variable. And you're testing a scale or continuous variable as the dependent variable. You basically do not want, you mean to avoid the inflation of one error, which increases with the number of comparisons you're conducting in your data. So if you have 3 or more levels and you compare 3 or more groups, you have an exponential inflation of your type 1 error. It's not just 5% as it is with one comparison. So it increases with each additional comparison, because for each individual comparison, it's a 5% error. So this type 1 error is basically then leading you to reject something just by chance. If you look here at the higher number of comparisons, it's basically higher than 50%. So this is, it's basically more probable than flipping a coin that you will make an erroneous rejection of your null hypothesis. So that's why this is important. We have here an overview and I flagged this table. This is important to understand in the greater scheme of things, which test to use with which research question or analytic question. With the F distribution, you're basically comparing the variance between the group. The variance between the groups to the variance within the groups. So that means the variance between the groups is basically the deviation of each individual group mean from the grand mean, which is the mean of means, which is the mean of all means. Whereas the within groups variability is the variance, it's an amalgamated estimate of the variance within each group. We have a one-way ANOVA. Between groups are basically hypothesis testing where you have more than two samples, i.e. more than two levels of an independent variable. Yes?
Sorry, is this 12 or 13?
This is 12. 13 comes in a second. Once we browse through 12, we get into 13. Yes, it is just a review from last time. Within groups that we're going to talk about today, the difference between the between groups and the within groups is that now with the within groups, that's basically the multi-level correlates to a paired sample t-test where you basically have the same participant going through different levels of the independent variable. And today we have an example for that where you basically have the same participant giving 3 different ratings of 3 different products, which will be beer today. It's independent sample t-test, we did wine, now we do beer. So I didn't come up with these examples. So we do the within groups ANOVA is also labeled a repeated measures ANOVA because you have the same participant at each individual level of the independent variable. You will more likely see repeated measures being quoted and referred to in the literature. If you read a scientific article, repeated measures ANOVA will be quite a frequent test that you will read about. You have 3 assumptions for the ANOVA. You have a random selection of samples, you have a normally distributed samples, and you have homoscedasticity. Homo means equal or the same in Greek, and it refers to the variability amongst the groups not differing from each other more than 20%. The 6 steps of hypothesis testing are kind of comparable to what we've done with the other hypothesis tests. You first identify populations, distributions, and assumptions. You state the null and research hypothesis. You determine characteristics of the comparison distribution, which is the F distribution for an ANOVA, which is a unimodal right-squared distribution with a critical value that you determine from the F-score table based on the degrees of freedom between and the degrees of freedom within that we have learned last week how to calculate or estimate or derive. We calculate the test statistic and compare it to our critical value, and then we're rejecting the null hypothesis based on the null hypothesis that we have developed. And these null hypotheses, so again, degrees of freedom between is the number of groups minus 1. Degrees of freedom within is degrees of freedom of each individual group summed up. This gives you the degrees of freedom within. Yeah, we determine a cutoff after the calculation of the degrees of freedom between and within, and we are then calculating an F, which is the ratio between the between groups variability, so the variance between the groups over the variance within the groups. This ratio is your F-score, and this you're testing against this distribution. If this exceeds your critical value, you're rejecting the null hypothesis, and you assume that under the research hypothesis, at least one of these groups is different from the other group. In a post hoc test, you determine which one is different. So we talked about this. This is how you have to look at it. You have a mean of means, which is the grand mean, which is the bold solid line. You have the group means. You quantify essentially that variability, that variance of each individual group mean to the grand mean, and this gives you the sum of squares and the variance between the groups. And then you quantify the variability within the groups around that group mean, and that gives you an estimate of the within groups variability, with the idea that you're basically quantifying that overlap between the variability of these groups. So you basically compare these groups in terms of the variability, and you bring it in relationship to the variability within the groups. You basically want to put this all together in a source table, the ANOVA source table. We will do that today in R, and this source table essentially will be kind of the same for all your statistical softwares, whether you use SPSS, SAS, R, Stata, whatever. This source table always looks the same. So this is really important that you understand how to interpret this. Even if you never do analysis again and you just look at printouts that the statistician did for you, that source table, this is where the money is. So you have in this column, you have the actual source. Here you have the sum of squares, the degrees of freedom. That's the actual variance between and within. And the ratio of this is your F. And this leads you to your decision. Good. This is the example we did last time. That was simple, right? Here, the calculations of the respective sum of squares, which we have done last time and continue today. This is the example. So we did that effect size. Keep in mind that there's an effect size, and the effect size here is the so-called R square. What is this R square? When you look at it, you basically have something that is smaller as a part of something that's bigger. So we calculated this last time, and we found an R squared of, I forget what the exact number was, but the interpretation of this is basically what proportion of the sum of squares of this total variability is basically represented or reflected by the sum of squares between. That means that how much of that variance between the groups, that deviation between the groups, contributes to this total variability, to the sum of squares total. And this fraction, it is literally a proportion. For the context of an ANOVA, it is the effect size of an ANOVA. In the context of regression, where you will hear again about the R square, it's called the proportionate reduction of error. Because in a regression analysis, you have error, and a part of that error is explained by your regression model. And employing the regression model will basically reduce the error that you see in your scatter, in your data, by basically explaining some of it. And that's what you do with a regression model. So there it is labeled a proportionate reduction of error. Here it is an effect size. But this is where ANOVA and regression basically intertwines, and basically comes together. So that's the R square in the books, and I've flagged this as an additional topic. Also look up what an omega squared is, because that's a continuation of the effect size, which basically has arithmetic adjustments routing to the number of groups and the number of individuals in there, that basically will affect the estimate of your effect size and will make it a bit more conservative. So thereby, you definitely want to know also what an omega square is. So this is a continuation of the R squared, and it also is a marker metric of the effect size. The conventions we talked about last time, the effect size of 1% to 6% is small, 6 to 14% is medium, and everything greater than 14% is large. You have post hoc tests, one we will see today in R. So you have a Tukey honest significant difference test, which includes the calculation of the Q, that is utilizing the so-called Q table to conduct the comparison, the hypothesis testing, with an adjusted p-value, an adjusted estimate of your type 1 error. You have a Bonferroni post hoc test, which is basically a pairwise comparison utilizing an adjusted p-value. And you will also do post hoc testing and the multiple comparison if you have planned them before you actually started running your ANOVA. Then you will also do these a priori planned comparisons. Otherwise, you will only do the postdoc tests if you actually had a significant result in your ANOVA. So that's the TACI, calculates here the Q, which is the HSD, the honest significant difference Q, calculates the difference between the groups of interest, M1 minus M2, M1 minus M3, M2 minus M3, depending on which groups you're comparing, divided by the SM, which is the variance divided by the sample size. Then you utilize the Q table to do the actual hypothesis testing, taking interpretations. Bonferroni divides the level, the P level by the number of comparisons, thereby derives a different alpha level that you will utilize for decision making, which is stated here. Any questions on this? That was just a quick recap. We did everything on Wednesday last week. Because if not, we can move on to our within groups ANOVA. The within groups ANOVA, or repeated measures ANOVA, is basically the equivalent to a paired sample t-test. Again, the distinction between the t-test and t-hypothesis testing and the ANOVA is that you have 3 or more groups. And with the within groups ANOVA, you have a paired sample t-test with more groups, with more levels of independent variables. It's called the repeated measures ANOVA, just like stated before. The really important thing which will prompt you to think you should use the within groups ANOVA is that it's the same participant that undergo each level of your independent variable. And this will be very obvious once we do the example today. What's notable in that is by taking the same individual at each level, you take out some of the variability in your group estimates out, because you have a certain level of variability, but just looking at the variability between the subjects. So you get now an estimate of what is actually attributed to the variability between the subjects and what is due to the variability between the groups. So you get more accurate in your estimate. Because subjects do have variabilities in all terms. So today we're talking about beer rating. So we have 3 groups of beer. We have cheap beer, mid-range beer, and expensive beer. And 5 different observers are rating this beer. So now the perception of beer changes between individuals, and it's different between individuals. And to kind of get more accurate in our hypothesis test, we're taking the subject-specific individuality or individual variance out of the equation. And this is how it's treated also arithmetically. So it reduces the error due to differences between the groups. The groups are identical for all of the relevant variables, because the only distinguishing factor is now really the group characteristic and not the individual anymore, because the individuals are the same. So we're taking the subject-specific variability out of the equation. Calculations are similar. We're calculating now, in addition to the between groups and within groups sum of squares, we're also calculating a subject-specific sum of squares. So that's the variability for the individual. By taking this out, we're essentially removing this subject variability and getting more accurate. The steps of hypothesis testing are the same. We identify populations, distribution, and assumptions, make our assumptions, which are random sampling, normal distribution, and homoscedasticity, which means that the variability between the groups is not differing more than 20%. Then we determine characteristics of the comparison distribution. We determine the critical values or cutoffs. Notably, these are done in the same fashion as with the between groups ANOVA. And the subject sum of squares that I've talked to about this variability for the subject is essentially something that is quantified, it's calculated. You even calculate an F-score for this variability, but it doesn't go into your decision process. Your decision process is just like with the between groups ANOVA, based only on that F, which is the ratio between between groups variance over the within groups variance. So nothing changes in that regard, despite this additional metric we're calculating. Okay, one caveat. And if we're going back to the paired sample t-test, we talked about the order effect. So the order within which a condition, a level of your independent variable is being administered plays sometimes, or in many cases, a role. And this is what you have to keep in mind, particularly when it comes to ANOVA, where you have 3 or more levels, and each participant goes through 3 different levels of your independent variable. You have an order effect, and this order effect you need to counteract by counterbalancing, as you know from the paired sample t-test when we discussed it last time. So for the example that we will do today with the 3 different types of beers drank by 5 different participants and rated by these 5 participants, obviously it may make a difference if you start with the expensive beer and then you have a cheap beer. Your perception of what that beer is like may be different. So one way to counterbalance is to have each participant start with a different beer at a different time, and you randomize them into starting with one beer over other beer. So that's kind of the idea of counterbalancing. Yeah, avoiding of order effects is actually a huge thing in these kinds of study designs. Counterbalancing and paying attention to order effects is a super important topic. But you will learn this in different contexts. Good. The null hypothesis of every ANOVA, as well as this one, is that mu1 equals mu2 equals mu3. So all of these 3 group means are identical. That's the null hypothesis. And the research hypothesis that at least one of these means is different. So now we have our characteristics. So we have 4 degrees of freedom this time around. So it's the degrees of freedom between. Maybe this is the point where we go to the example. So there's a spreadsheet on Canvas. So you have 3 PowerPoint presentations on Canvas. You have an F-score table in the module. You have an Excel spreadsheet on the table, on the module. And you have practice lab for the solution on your Canvas. So now let's start with the Excel spreadsheet. And you have here 3 different tabs. The first tab we did already. I didn't upload the completed version, but you have the completed version as an announcement. When we're looking now at our spreadsheet, so let's start off with determining the degrees of freedom. So we have here 5 participants drink 3 different beers and rate these 3 different beers on a scale from 0 to 100. Degrees of freedom now, of degrees of freedom of the groups, degrees of freedom between is now n minus 1. So the n groups, so the number of groups minus 1 gives us 3 beers minus 1 equals 2, right? Then we have next, we have degrees of freedom subjects. We have 5 people testing these beers. That gives us 5 minus 1 again, gives us 4. Now we have degrees of freedom within. And this is a little different than last time, because now we have an equal number of participants. We know that degrees of freedom subjects is 4. And now we're calculating the degrees of freedom of subject 4 multiplied by the degrees of freedom between, which is 2. So 4 by 2 is 8. And lastly, we want the degrees of freedom total, which is essentially the sum of all of this together. So we have 15 entries. So we have 5 participants in 3 groups, that's 15. And we calculate this as 15 minus 1 is 14. And here I just want to draw your attention to 14 as degrees of freedom total is degrees of freedom within plus 4 degrees of freedom subject plus 2 degrees of freedom between. 2, 4 is 6 plus 8 is 14. So again, there's this arithmetic dependency that will be important for you to know for homework and the quizzes. So these are the degrees of freedom. That's how you determine these. So now you understand the population, you know the comparative distribution, you know based on these degrees of freedom, and maybe let's do that right away. Based on these degrees of freedom, you can also say already in your comparison, you can now as a next step basically go not on the syllabus here on the degrees of freedom on the F-score table. You know now that between groups degrees of freedom, and these are the degrees of freedom in the numerator, are 2. There's 3 groups, -1 is 2. In the denominator, we have now so these are our degrees of freedom within, which is 4 multiplied by 2. That's 8. So now we have 2, and now we need to find the corresponding denominator of 8, which is here 4.46 for an alpha level of 5%. Makes sense, right? So degrees of freedom in the numerator, that's degrees of freedom between, that's 2. And you go down until you have a degrees of freedom within of 8. And then you align this with the corresponding alpha that you're willing to accept. So that's 5%, gives you 4.46. This here? Yeah. That's 8.
How I use that?
So you have your different alpha levels, right? So that would be 10%, that's 5%. It's 2.5, 1, and 0.1. And you basically are following along with the alpha level you're willing to accept. So if it's 5%, you are here within the row of 8. You basically follow it until your degrees of freedom between is at that level you're looking at. So if it's 2, and degrees of freedom between, and that's in your spreadsheet, or should be in your spreadsheet, would correspond with 2. And there you find your corresponding critical F value.
But why would you use row 8 versus a different row?
Which one would you use?
No,
No, because the commonly accepted type 1 error that you're willing to accept is 5%. Just like with a t-test, right?
but like in row 9 and 10, there's also 0.5.
Which one?
Like I'm saying in all the other subsequent rows, there's also 0.05.
Yes, but the F-score is different with each. So you have here, you have a smaller F-score. So if you have more degrees of freedom, you basically, your F-score criterion shrinks because you basically determine this critical F-score based on the degrees of freedom. Because if your degrees of freedom gets higher, arithmetically your variance, as you know, is being the sum of squares divided by the number of degrees of freedom, gets you to the variance. So your variance will be smaller with a higher level of degrees of freedom. Thereby, you're adjusting your critical F according to your degrees of freedom.
But you would always use the numbers from row 8.
No, you
Right, which is why we're looking at how to.
no, that's between. That's within.
Oh.
You remember, it's like the t-score table in a way.
Yeah.
It's just because it's more than 2 degrees of freedom we're interested in, because we also need to pay attention to the numerator. Now it's basically 2-dimensional in a way. Yeah? Okay. Good. Any other questions? No? Okay. Okay, degrees of freedom, F-score table. We know now 4.46 is our critical F. So let's note this down that we don't forget it. Critical F is 4.46. Now we go back to that. Good. So now next we want to calculate now our different sum of squares. And these look now a little bit busy, but they're actually not that terrible. So you have, just like with between groups and over, you have sum of squares total is calculated as the sum of squares of x minus grand mean. Sum of squares between is basically, again, just with the between groups and over, it's like each individual group mean minus the grand mean for each entry, for each x squared, gives you the sum of squares between. Now, new is the sum of squares subject, and that's now the mean for each participant minus the grand mean. And we will get to that, how to calculate it. There's a trick and super simple. And the sum of squares within is now, and this is now the sum of squares subject actually is operative, because we're calculating now within as the difference between total, between, and sum of squares subject. So this is where sum of squares subject takes out of that variability we use for the estimation of within. The idea of that is that we're taking this subject effect out of our estimation of the within, and thereby the ratio between groups variance and within groups variance gets more accurate and gets focused only on the actual difference between the groups, but takes out this subject effect. That's now the beauty of the within groups ANOVA. And this is why generally, if you have a chance, it's like a repeated measures, ANOVA is actually a very accurate and very accepted test in scientific methodology. So now let's maybe bring that over. It's a little easier when we right away see all these calculations. Let's copy that on a spreadsheet. So let's copy that in here. So what we need to do now, and this is again the part that is a little bit more laborious. So we need to bring again our data in a long format. And that's usually a little bit involved. So we're copying now the first two lines, then we're just duplicating this, and this becomes now beer type, because this was the cheap beer, right? So now we have the first estimate, then we just copy the second estimate, and this becomes our mid-range beer. And then we lastly take our high-end beer. We copy that down there. Now we have high-end beer. Oops. So if we're just quickly propagate this all the way down, we're basically getting now our long format. So this is the beer type. This is our rating. And now let's calculate these, a little space. Because you can quite easily calculate now your means. So we need a group mean, a participant mean, and a grand mean. That's all we need. That's 3 calculations. So we need now first group mean. That's simple. You just calculate the average for each of these groups. And that's already what you need in that regard. So we have now 3 different means. We see that group number 1 and group number 2 are barely different. Group number 3 is substantially different. When you want to calculate a participant mean now, that's equally simple. The only thing you need to do, you need to calculate an average for each participant. That can easily be done like that. So you basically just calculate the differences between these individuals. And you see that there are differences between those individuals where this participant number 5 was a rather critical beer drinker, whereas participant number 2 was more like a less critical beer drinker. So that's.
How did you get the participant mean?
Oh, it's just the same formula. You do average, and you just go across all the ratings of that individual. And now it's simple, right? So the only thing you need to do now you need to align now your estimates with the data you have here. So if we want to calculate now our grand mean, oh no, wrong. Let's do the grand mean first. Grand mean is basically the average of all of these estimates. That's simple, right? That's the GM. Now you want here, what you want to align now here is the group mean and the participant mean. Now this is in my way. Move that. So group mean, participant mean, simply all you have to do, you just bring the group mean down here. So okay. You basically press Command and C, you do Command and V, and you enter it here. Just pay attention to the paste values. You do the same with the second group. Again, paste values. And you do the same with your high-end beer. Paste values again. And now you just need to fill the blanks. You basically just need to copy this down. So that's simple, right? It's super simple and a simple calculation. So even easier is for the participant mean because that's aligned already. So we just need to press Command V. We bring this down here. We go again, paste values. And now we just copy it down here. And that's already all we need to do. It's simple. I know it was a little fast because we're a little bit on, it's a little time sensitive today. But basically you have now aligned your group means with each respective group, and you have your participants means aligned with each individual participant. It's just collapsing it in a way. And that's just like, unfortunately, in data analytics, the most laborious and annoying part is to get this data in an analyzable format. Those of you that are analytically inclined that will do that at one point in time, that's unfortunately the bitter truth. Is like, that's the real annoying part. Once you have your data in the right format, like building the models, that's like a breeze. That's like a lot of fun, actually. So it's really like getting the data in shape is annoying. Okay, but now we're at this step. So now we have everything already in the format which we needed for this analysis. We want, and this is the outcome, we want sum of squares. We want these sum of squares. And that can simply be calculated as this total is now x minus grand mean. This is the x, right? That's the individual rating. Minus the grand mean. But you need to lock this cell in. And now all you have to do, you have to just propagate this all the way down. Obviously, you need a sum of squares. That means you need to lock this formula in, and you need to square it. Otherwise, okay. So these are now your squared deviations. And summing this up basically gets you an SS total. So sum of this is basically a sum of square total. So that's 2117.73. So that's the sum of all squares. If you continue now, you basically, okay, so this is, let's rephrase this x minus gm squared. So from accurate. Now we need next, we need sum of squares between. So sum of squares between, let's move this again. Sum of squares between, it's m minus gm squared. So gm is grand mean, m is the group mean. So all we need to do is m minus gm squared gets us to group mean minus grand mean, oops, almost, in parentheses, squared, locking this in. That's all we need. Goes all the way down, not this. Now we copy this over there. So that's our Excuse me? X minus GM versus M minus GM. The difference is that X minus GM is this number minus this one, and that repeated for all the other ones, squared, each individual one. And the M minus GM is our group mean, each individual entry of only the group means, minus the GM squared. So you basically, you take one constant, which is your grand mean, and you use this as your reference value, because no matter what sum of squares you're calculating, your reference here is always the GM. So you're only looking at either the total variability of each individual score or the variability of these group means from the grand mean, or the difference of the participant mean from the grand mean. So this is how you capture this variability, and this is how you build these relationships, these ratios that you then need for hypothesis testing. So it's the principle is only that the reference point is your grand mean, and this is when you remember this. When you remember this, and this is the nicest way of depicting this. So this is again from the dictator example. When I look for the graph, I never find it. Oh yeah, this is the same principle, right? So you're calculating based on the grand mean as the reference. You're calculating the variance of these individual group means from that grand mean. Then you take each individual point and calculate the variance to that group mean. And now you just have the different participants. That gives you, for our beer drinker example, it gives you 5 different means, and you calculate the variance of these. And then you take all these points and you bring all of these sum of squares together, and you're comparing all of them together and calculate the ratio between and within variance. Make sense? Yeah? Sure. Okay, sum of squares subject. This is now the participant mean. Participant mean minus the GM squared is now the same principle. Participant mean. Participant mean minus grand mean, locked in with the dollar sign, squared. And now summing this up gets us now SS participant, gets us now these 3 sum of squares. And now it's simple, right? So now we're calculating the sum of squares within by taking the total minus the sum of squares between and the sum of squares participant. And this is now this minus this, oops, minus the sum of squares participant, which becomes an explanatory factor and takes out of the inaccuracy by the inter-individual variabilities. I'm flagging this again. You remember how when we talked about graphical displays of data, we talked about interpolation and extrapolation, where interpolation was between 2 points and extrapolation was beyond 1 point. So that was where you continue the function and you extrapolated it beyond the point of data you had available. So I'm saying this because you have extra, which is outside, then you have inter, that's in between, but you also have inter between, and you have intra within one individual. So you are meaning to capture here by quantifying the intra-individual variability within one individual. You're trying to capture overall this inter-individual variability caused by each individual subject and its repeated measures. You mean to take this out of your total variance and thereby increase the emphasis on just quantifying this variance between the groups and just utilize these for hypothesis testing, taking the subject effect out of the equation. So So now this being said, we have now everything to complete an ANOVA table. And the ANOVA source table always has a source column, which is between, subject, within, and total. This being said, next we have sum of squares, which we know between is now this. The subject sum of squares is this. The within is this one. I want to label this. This is within. And the total is the biggest one here at the beginning. So that's the second column of our source table. Now next we can go to the quantifier degrees of freedom. We have these already here. We have between, subjects, within, and total. You can just copy this down. That's our degrees of freedom. And now to come to the variance. This is now nothing else but the sum of squares divided by the degrees of freedom. And this is true for all four estimates. So if you know these arithmetic relationships, you're set for ANOVA. You need to understand what the source table contains, how you got to each individual one of them, and this is the slide where you basically you have the calculation right here on that slide. And last, you just need to calculate the F scores. And for the within groups ANOVA, we have two F scores that are relevant. First one is, as always, the between groups F, which is between divided by within, which is a 14.77. Second, we need an F for subject, which is subject variance divided by within, which gives us a subject F of 4.93. So that's all we need. Simple, right? And so based on this calculated F, would we accept or reject our null hypothesis? That's the critical F. Yes or no? Are we rejecting or accepting? Are the differences between the beer ratings in the different groups? Well, the F is larger than the critical value F, right? So we're rejecting the null hypothesis. So we accept the research hypothesis that at least one of these groups is different. And when we look at our group means, we see tremendous variation here. There's quite some variation in the participant means. So there's one that rated basically every beer like as being an outstanding beer. Then you had one who was like super critical with the beer. So there's huge inter-individual variability. And if you look at the three different group means, you see not much difference here between the first two groups, but you see tremendous, great, large difference between the high-end beer. So that basically also kind of like gives us an idea already which group mean is going to be different, right? But we can essentially quickly quantify that, and well, we will do that in R essentially. But yeah, let's continue with this. So we can compare the group mean differences. Then was a post hoc test, which we will see in R. Okay, so these are the calculations. Once again, these are the individual variances. Then calculating the individual F scores gets you to have those F scores which you compare to your critical F. If it exceeds this critical F, you're rejecting the null hypothesis. Lastly, you basically need to estimate now the effect size, which is now again the fraction of your sum of squares between as a fraction of your sum of squares total. But now this time around, in addition, it removes the effect of the subject. by subtracting the sum of squares subject from your total variance, or total sum of squares. So if we do this now for our example, it's going to be r squared r squared is basically sum of squares total, sum of squares between, divided by parentheses sum of squares total minus sum of squares subject. Gets us to an r square of 0.79, which we know is a large effect size because it's greater than 14%, which is the threshold, that lower threshold of large effect sizes. So basically there is quite a large difference between those groups. And not surprisingly so, because it is essentially with 34, 34.6 and 52, that's quite a difference. Good. Any questions on the calculations? It's quite intuitive, right? It's, you just need to know the equations to actually calculate this individual sum of squares, and then know how to actually get from that to calculate your within, and then just calculate the ratio between sum of squares between and sum of squares within. Then you get the ratio, yeah. Now what do you do with the ratio? You compare it to your critical F. Correct. The ratio is the F. Good. Don't forget in this context, you have, with the F distribution, you have unimodal right skewed distribution, where your critical F is somewhere on the tail and basically constitutes the p-value, which is to be found beyond your calculated F. And if this exceeds your critical F, your p-value, your calculated p-value is smaller than your type 1 error that you're willing to accept, the so-called alpha, which is in most cases 5%. And then you will basically reject an null hypothesis if it's smaller. Okay, so that was this. Any questions to any of this? I know it's a lot of calculation, and it's not the most straightforward calculation, I'm well aware. But it's important in this context to understand the concept and to also understand how to derive this respective calculations. So this is not a Tucky honest significance test. We can just quickly do that. So you can do this now. And we will do it in R in a bit for practice lab 4. You can essentially, your SM is now calculated as your MS within, which is your variance within, divided by your N, which we know is 15 in a square root. Oh, 15, not 16. Square root. So this is 1.57. So if we're calculating now 3 different Qs, and that's the Tucky, right? So Tucky HSD is now M1 versus M3, M1 versus M2. Oh, should do it the other way around.
Which means are that?
Those are the group means. Oh. So these are the group means. So Tucky So go back to the null hypothesis. And the null hypothesis we said that group M1. So if we quantify, if we state express formally the null hypothesis. So the null hypothesis here is M1 equals M2 equals M3. So the research hypothesis, the alternative hypothesis, is now that at least one is different. So at least one is different from another M. So that's our research hypothesis. And now we want to find out that this is post hoc testing. We are basically now calculating a Q, which is an adjusted estimate of these differences and the probability of this being different. And we're finding out now which one is different from which one. So we have three different means, which is M1 versus M3. That's comparison number one. M1 versus M1, M1 versus M2 is the first comparison. M1 versus M3 is the second comparison. And M2 versus M3 is the third comparison. That's how we can distinguish these differences, right? And M2 versus M3. So calculating this now through is now the difference between, and here you have to be careful because essentially you're quantifying here. So you're doing now this M1 minus M2 in parentheses divided by the SM. So that gives you here a small, actually you need to look at an absolute value. Gives you an estimate. So if we're calculating now M1 minus M3, again, absolute value divided by SM gives us now a larger number. If we're calculating now M2 versus M3, again, absolute. Well, we see already what the differences are, right? So now based on that, you can say where the largest differences. And then you have, and we have looked at this last time. So what is it? So here you have also for a formal comparison, you have with the Taki. So this is a Taki on a significant difference test. You're calculating here a Q, and you have here a Q table in which you basically, you can look up your within groups degrees of freedom. And you can basically formally compare them and see whether it rejects the null hypothesis or not. So this isn't adjusted, but basically on, so this unfortunately doesn't contain that range that we have, but essentially we know already that these two will be significant. We don't even need to further go anywhere because we know they are equal in magnitude. And we know from the ANOVA that they are significant. So these two are the ones that are significant, and they're essentially comparable in magnitude. So we know now that M1 and M2 are significantly different from M3. So that's Taki, and that's an adjusted post hoc test. Good. What next? So this is Taki. We will also do this in R in a second. And lastly, Nolan and Heinzen want us to briefly talk about so-called weird samples, which I personally have never heard that term, but they want to emphasize that not all studies and all analysis from Western, educated, industrialized, rich, and democratic countries are essentially generalizable to every target population on planet Earth, because in different settings that are not falling into these five categories from societies that are not in one of these, not meeting one of these five criteria, are mainly not generalizable to the global population. So therefore, they call for a constraints and generality statement, in which basically a statement about the target population is meant to be made. And basically, you mean to state that there are certain characteristics to this population that may not be found in other populations that you may utilize for studying whatever dynamic you're reporting. So these are weird samples. And good reporting practices basically includes these constraints on generality. But we've talked about generalizability and we've talked about those aspects. So here they just mean to emphasize that this needs to be stated explicitly in every publication you mean to publish. Good. Any questions on any of this? Yes.
Before, when you said that M1 and M2 were significant, how come those ones are significant if the difference was between that and the 3?
Once again?
In the Excel spreadsheet that
Yeah.
you did like that test.
The Q test, yeah.
The M1, yeah. So how come M1 versus M3 and M2 versus M3 is? Oh,
Because when you look at the means, so M1 versus M2.
okay, I thought you were saying that M1 versus
No.
M2 is the significant limit.
No, it's M1 was M3 and M2 was M3. Did I have a misspoken?
I just misunderstood.
No, I may have misspoken. It's like I always had a long day. So it's possible, but yeah. So basically where the Q is larger, you basically see a significant result. And if the Q table shows this to be exceeding, your Q exceeds that critical Q, then you would reject the null hypothesis of this being different, of not being different. Good, thank you. Okay, if nothing else, we can turn to practice lab 4. And practice lab 4 comes with a little bit of a peculiarity today. And so you see essentially that the practice lab per se is identical with the examples which we did in class. So we're basically looking again at the dictator game. We're comparing these for societies against each other, and as a between groups and over, and we're also going to do it within groups and over. So these two examples are essentially in the practice lab 4 solution script. You can download this from your module. The peculiarity is that you will be installing packages. So if you open that script, I would like for you to first run line 2, where you remove everything from the environment. Next, I would like you to run line 5 and 6. Don't copy what's written here, just run line 5 and 6. This will prompt your R to do a lot of funny thing in the console. And nothing terrible is happening right now. It's establishing a connection with a server, and it's installing a package. This runs all by itself. You don't need. No, it's minimal. It's minimal. What was the question?
Was I supposed to click install?
Yeah, you can do that too. Yeah.
When I ran my 5 and 8, I asked if it's small.
Yeah, you could have pressed install. It comes to the same thing. The only thing is like we're using, and this is R as it stands like this is the core version. This is the core version of R. This is basically, it's coming with the standard functions. So I want to show you this with some more advanced packages, with functions that are contained in packages. So essentially, the way you have to think about R, you have a base R, which is like the core software. Yes.
Are we gonna do this while together next class?
No, we're doing it now.
In the next 2 minutes of the process?
We have 17 more minutes. We don't?
It's 1 minute.
Oh, no. Okay, we can do it in 2 minutes. Just install for now and press the hashtag button. You just need to run the rest of it and then just submit it in the same format. Please make sure to, after you render installation, hashtag it out and save this downloaded file.
Where's hashtag value?
So just put a hashtag in front of the install.
Before we press control.
No. First run it, install it, and then comment it out. Once you have installed it, yep, run the whole thing through.
Keep it as
that doesn't
hashtag for 5 and 6.
Yes, but first, after you ran it and it's installed, it's all done, then you hashtag it out there.
Does that make a difference? Does that make a difference in the console?
No, it will not run it again. So after you installed it the first time, you can hashtag it out because then you can run the whole thing again and you never have to install it again.
Everything, even it has this like all the URLs that it's.
Yeah, that's fine.
After it, what do we do?
Hmm?
What do we submit?
Well, the console. You just run the entire code. Hmm?
This part,
This one?
I thought you hear the whole thing.
Yeah, just hashtag 5 and 6 out and run the
Here.
I want to press my command L.
command L. Yeah. No, control L. Sorry.
Well, sorry. Does this look right? Like this ending, the height?
Yeah, that's
Yeah.
yeah.
Okay, perfect. And then I forgot what it is. It's STAT 1021.
STAT1021, your family name and practice lab 4.
So you want us to copy this?
Yes.
Can you run again?
Yep. So run these 2 lines. Did you run those? Install 5 and 6.
When you do that, and then
Yeah, that's perfectly fine. But you hashtagged it out? Perfect. That you can submit. Open a text edit file. So again, once you have that, just a second. Once you have that and you're running this down, you click into your console, you press Control and L. You go in the script, you press Command and A, you press Control and Enter. Please do not neglect what I'm basically giving you here. Have a look at this because essentially it is what we did over the last time. I will talk about it again on Wednesday and I will walk you again through this. So here we have text edit. You create a new text edit file. You go new document, you copy it in here and you save it as STAT1021. Your family name and practice lab 4.
we could see the printer without it. Down.
What was the question?
I can save it with or have it downloaded.
No, you need to run the packages. You need to install the packages.
But after I hashtag it, then.
So you installed it?
Yeah.
Okay, then hashtag it and then run it again. If
That's what I submit.
exactly. Yes.
Sorry, what was the first that you said? Click
Yeah,
enter?
just install it. Just install
Click
this.
enter?
No, install this.
What is that? Oh, install. Okay,
That's
now
an
what?
alternate way to do it.
Okay.
That's the wrong file. You need to download practice lab 4 solution. So let this install in peace. So there's a solution file on. Yeah, you're in the wrong. You need to go
It's
back. You
practice
need to
lab,
go to
so-
the module.
So Professor, I just submitted my, but I just don't know if I did it right, but I think I did.
Yeah, so the practice lab 4 solution, don't go into files, go into module. And the module is the actual file that is, yep.
Mine's not, it didn't go.
Install this.
It will look bottom, it's on, yeah, it's on there. It's
Yep.
on MA.
Okay, that's fine.
It's under which week?
So now, the current one, 20, module 20.
Thank you.
You need to do this and this, this and this. This is the Bear's comparison. Here you have the deploy analysis. That is the pipe, that's deployer. So you have it all done. You just have to copy this.
So now I can
Yes,
just
yes,
do text edit?
Yep.
Or, and then I can submit it? Okay, so now what do we do from here?
Does this look right?
no, this is the wrong file.
Oh, what?
That's the wrong file. You need the file from the module. No, you need the solution file from
Okay, so
module.
is this the right?
You're all going